This paper is about static action recognition by efficient greedy inference. The authors are Shoka Dabidi, Massimo Piccardi, Marianne Williams from University of Technology, Sydney, and the paper is presented by Hassan Gassemi. Our goal is to recognize actions in still images. The way we intend to do that is by exploring the relationships between the various image parts. Most of the existing approaches categorize either as using some kind of aggregated descriptors or feeding articulated human models. Our approach divides over the following stages. First, we segment the image into its set of superpixels. Then for each superpixel, we extract a rich feature vector. On the side, we train a set of object detectors. We are using the MSR21 dataset for that. We 23 object categories. And then we pass each superpixel to the object detectors to score the posterior probabilities of each object class. So for each superpixel now we have a vector of 23 probabilities that we use as the measurement for that superpixel in the following steps. After finishing with the measurement process, we start with the inference. Over our graphical model, we form a fully connected graph of pairwise edges between all superpixels, and we infer their classes and the class of the action jointly. Our approach is summarized by this picture. At the bottom, we have the image partitioned into superpixels. Each superpixel is assigned a measurement, which are the posterior probability of object classes computed individually over each superpixel. The intermediate layer is the layer of the class labels of all the superpixels, which are inferred jointly, and the top variable is the action class. So inference over a fully connected graph can only be approximated, and we use an approach which is very similar to loopy belief propagation, where we maximize marginals iteratively. Here we propose two optimizations. The first is to compute only the terms which are strictly needed for the argmax, and the second is to cache common terms over successive nodes. Full details can be found in the paper. As a result, we have a significant speed up of the execution time. The average time per iteration with the native implementation, which is OT squared, is 542 milliseconds. With the first optimization, which is an OT algorithm, is 480 milliseconds. And by using both optimizations, the average time per iteration is only 2.5 milliseconds. As accuracy, we have carried out experiments over Stanford 40 actions, and the mean average precision we have achieved is 72.3%, which is a major leap over the best results to date, of about 17 percentage points. As discussion conclusions, so we have recorded a big improvement in mean average precision on Stanford 40, but as caveats, we have used another dataset, MSR21, to pre-train 23 object detectors. On the other hand, we have not used the bounding box information, which is provided as part of the annotation of Stanford 40. The approach is promising for actions that can be fully defined by the context, not from the pose of the actors. So it cannot be used without a scene or background, and could not be used for detecting multiple actions within a single image. So probably the future work could be to hybridize this approach with an articulated approach like the formable part models or the like. Thank you very much for your attention.